what we're going to do is we're going to start looking at using our third method for determining enthalpy change of a system using what's called our standard enthalpy of formations. Now, our standard enthalpy of formations come from what we call a formation equation. This is just an equation where I form 1 mole of a compound from its component elements in their standard states. So for example, here, I'm going to form 1 mole of my aluminum sulfide, and aluminum sulfide consists of 3 elements: aluminum, sulfur, and oxygen. So you can see in our reactants I have aluminum, and in its standard state it's solid, sulfur, which in its standard state is solid, and oxygen in its standard state, which is gas. Now you notice that there's fractions in my reactants. This is because when we balance our formation equations, they're based on 1 mole of product. So if that's the formation equation, my standard enthalpy of formation is just the enthalpy change for that reaction. So let's take a look at another formation equation. So if I ask for the formation equation for our lead 4 nitrate, then to do this, the first thing we would do is we would write 1 mole of the compound in our products in its standard state. Then we're going to write each of the elements in their standard states in the reactants. So lead is solid metal at room temperature. Nitrogen and oxygen are both diatomic gases. And now we're going to balance them with the idea that we're going to keep the coefficient in front of our product, the lead 2 nitrate, a 1. So therefore, I would balance the equation based on that. Now, the standard enthalpy of formations are useful because an application of Hess's law to a series of formation reactions allows us to distill down to this simple calculation, where the enthalpy change of any system is equal to the moles of each product times their standard enthalpy of formation minus the moles of each of the reactants times their standard enthalpy of formation. So let's take a look at a specific example so we can see how this works. So here, the main component in laboratories or heating homes is methane. What's our molar enthalpy of combustion for methane? So when we do these, we have a number of different things to do. The first thing is we always want to make sure we have a balanced chemical equation. So here's the balanced equation for combustion of methane. And then the next thing what we're going to do is, as we always did, we summarize our givens. And so what we can do is we can go to a table and we can look up our standard enthalpy of formation for each of the elements, or sorry, compounds. And so we could go to the table and look up my standard enthalpy of formation for methane, and we'd see that it was negative 74.4 kilojoules per mole. We could look it up for carbon dioxide gas, negative 393.5 kilojoules per mole. We could look it up for water, and we could also look it up for oxygen. But we wouldn't find oxygen on the table because it turns out that the standard enthalpy of formation for any element in its standard state is 0. So once we have our givens, then what we can do is we can take our generic equation and we can apply it to this system. And so what we have here is we have the application to this system. And so what we can see is we have, for my carbon dioxide product, it's the moles of carbon dioxide times its standard enthalpy of formation plus the moles of water times its standard enthalpy of formation of water. So that's my products minus the moles of methane times its standard enthalpy of formation plus the moles of oxygen times its standard enthalpy of formation. This is my reactants. So now if we take our values and we substitute in, we can see from our balanced equation we have a value of 1. We have a value of 1. So 1 mole times negative 193.5 kilojoules per mole of CO2 plus 2 moles of water times negative 285.8 kilojoules per mole of water. And again, this constitutes my products minus my 1 mole of my methane times negative 74.4 kilojoules per mole of methane plus 2 moles of water times its standard enthalpy of formation, which is 0. And so the per moles would cancel out, and we're left with just kilojoules. And then I would just add the values together, and we get a enthalpy change for the combustion of methane for the balanced reaction written above of negative 890.7 kilojoules. Okay, so let's look at another example. In this example, we're told that the molar enthalpy of combustion for benzene is negative 3,273 kilojoules per mole of benzene. And we're asked, what's its standard enthalpy of formation? Likewise again, just like before, we write out a balanced equation, then we write out our given. In this case, we don't know the standard enthalpy of formation of benzene. We can take our equation, and the enthalpy change for this reaction would be the moles of product times their standard enthalpy of formation, so the moles of CO2 times its standard enthalpy of formation, plus the moles of water times its standard enthalpy of formation, minus the moles of reactants times their standard enthalpy of formation, so the moles of benzene times its standard enthalpy of formation, plus the moles of oxygen times its standard enthalpy of formation. In this case, we have currently two unknowns. We don't know our standard enthalpy of formation for benzene, nor do we know our enthalpy change for the reaction. But we do know our molar enthalpy change. And because our enthalpy change is equal to moles times our molar enthalpy, I can take my coefficient here of 1 for the balanced equation, and I can substitute it in, and I get that this balanced equation as written would release 3,273 kilojoules. So my delta H is negative 3,273. So now that we know our enthalpy change for the reaction, we can then now take and substitute our values into our equation. We know that we have 6 moles of CO2 produced, and its standard enthalpy formation, plus we have 3 moles of water, its standard enthalpy formation. 1 mole of benzene underwent the reaction, its standard enthalpy formation, plus 15 over 2 moles of oxygen times its standard enthalpy formation. And so then we can gather our like terms and solve, and we see that 1 mole of benzene times its standard enthalpy formation has an enthalpy change of 54.6 kilojoules per mole. And so if we isolate our standard enthalpy formation for benzene, we find that its standard enthalpy formation is 54.6 kilojoules per mole of benzene.